Sure. Yes. Okay. Hi, everybody. Thanks for having me. I'm so sorry I cannot be there. So thanks, Mark, for inviting us here. So this is, again, a collaboration, of course, a presentation with amongst of our colleagues, my colleagues. So a quick presentation today to talk about how modeling can be useful, hopefully useful for emergency response. So I'm going to talk about, let's say, our expertise as modelers. So I'm going to go quickly through this. I know this is being recorded and we will share then later on my presentation. So I'm talking on behalf of RPS Ocean Science. So we are a group of scientists, environmental engineers, etc. We've been doing modeling for the past 40 years. So we've been doing numerical modeling to answer environmental problems in the environment, marine environment, coastal environment, air. We developed tools, we implemented models to try to understand the risk, right? We talk about risk for a while now, to understand how some of these pollutants will behave, right? Whether it's oil or other type of chemicals, but also to help responders to mitigate impacts, right? So keep that in mind, right? That the modeling is not just to do a forecast, but also to understand complex behaviors and to help design mitigation measures. So I'm going to go right away into the presentation. I'm going backwards, actually. Key messages. So let's start with the end in mind, right? We wanted to pass some optimistic or realistic optimistic message to say that the science nowadays allows us to understand, right, what's the behavior of some of these chemicals. Those are not really new chemicals. What is new is maybe the way we are handling, the way we are going to be using those. So from a modeling point of view, there is a relatively good knowledge already of how these chemicals behave. What is challenging is to understand, right, what are the release conditions and to be able to run these models in a fashion that could be useful for emergency response. So there is a more complex process coming in terms of the shipping, but modeling can help you guys. So in order to improve the response from our point of view, from a modeling point of view, I think there are two key elements, which is first understanding the risks, right? So modeling can help on the risk analysis to help improve the prevention, the planning. But the second component is that models need to be integrated, right, into emergency response systems, into dashboards or common operational platforms. I think some other colleagues have mentioned this earlier, right? So modeling is one piece of information that needs to be fed into a common operational picture, right? So the second aspect, kind of key message for us is that regarding specifically in these new chemicals, let's call them, or new potential risk products, is that there is a lot of learning already happening, right? So in Europe, at least that we're aware of, that we are involved, there are European funded projects for chemical spills in the marine environment, for example, Manifest, or for these low sulfur oils, IMERUS, right, to understand how these products would behave if spilled in the ocean, because their particular compositions make it very hard to recover those from the ocean. So there are projects already happening that we all could be learning. So sharing information, sharing knowledge is important. In terms of improvement, right, our models, anybody else models can be improved using data from field trials, from laboratory assays. So that's important for us as modelers to connect with the reality, right? To keep feeding and improving our models and their usefulness connected with the responders, with emergency responders, right? The last component in terms of teamwork and capacity building is in times of response, let's say, it's critical that models, again, needs to be connected with observations, whether it's remote sensing, whether it's ocean state, wind observations, or drones, sensors, whatever it is, it's critical to connect observations with the model prediction so that one feeds the other, right? It's a cycle of monitoring and prediction. One feeds the other to help improve the model predictions, as well as helps the responder to understand the situation, what's happening, how it looks like, right? So going into more specifics about pneumonia and how we use models to answer this complex problem. So specifically in terms of ammonia, a little bit of chemistry here, right? We made a simple diagram here to understand that specifically ammonia, looking at the potential use for bunkers, right? Typically transported from a gas, if gets released, this gas liquefied, right, get released into the environment, likely going into the atmosphere, potentially going into the water column. So there is a behavior, it's a change in behavior, a change in phases, in changing in reaction, and different effects will depend on a bunch of different things. So ammonia could become an NH3 or an NH4 with different levels of toxicity at short, long-term effect, depending on the release conditions, depending on the receiving waters, depending on the temperature and the original pH. So by itself, ammonia could behave in different ways. That's what becomes a little bit challenging. If we look at looking at the atmospheric component of it, right? Ammonia gas releases on land, so let's say on the atmosphere only, can be simulated using multiple different tools. There is easily a half a dozen software or modeling packages that looks at the concentrations of ammonia being dispersed into the atmosphere. Usually those are, let's say, simpler problems because they are single point, steady state conditions, right? That looks at how a plume would evolve. With these tools, right, we can, let's say, more or less easily define exclusion zones. These type of models can help us understand the risks, right, to understand plan for prevention. Important element here to mention is that it all depends on the concentrations, right? What are the thresholds that we are looking at? I'm going to mention this a bit in a second, right? So for us, for the modeling point of view, exclusion zones needs to be associated with exposure levels for how long a certain concentrations have been present in a particular spot, right? Now, things get a little bit more complicated when it's a matter of the water, how, as I said earlier, ammonia being released in the marine environment, whether it starts at the air because it's a tank failure that liquefied ammonia falls into the water, or whether there is a release below the water surface, right? It goes through different processes. So the first thing we need to understand is the release conditions, right? Again, how this particular pollutant enters into the different compartments of the marine environment, air and water. We need to have a good understanding of the environmental conditions. So in other words, the winds, the currents, the waves, etc., temperature, salinity. And then the modeling, then the results of this modeling will depend highly on the thresholds of concern once again, right? So on the map here, we see an example of what we do is a stochastic analysis. So we run hundreds of cases of, in this particular case, ammonia spill, NH3 in particular. So it presents the concentration. Based on a particular concentration level, we can map and generate these maps of probabilities as a function of release conditions, as a function of environmental conditions, right? This is, I'm going to jump to another one. I think there is a possibility to show the animation. This is one of the tools. Of course, doesn't want to show the animation. So I want to go back. So these are screenshots. I think I've seen screenshots earlier. This is one of our software. It's ChemUp. So ChemUp is a three-dimensional, time-varying modeling system that tracks chemical spills in the environment. So as I said, in order for us to be able to do predictions, we need to have accurate information about the release conditions. The behavior of this pollutant will be very different if it starts at the water surface, below or above, right? But we also need to understand the environmental conditions, whether the winds and currents, how they behave, right? And then the results could be quite rich information in terms of the concentration in the water column, in the atmosphere, as time series, but also as exclusion areas, right? So this is in terms of water modeling, concentrations. Oh, here we go. Surprise, surprise animation. What is important for us to pass the message to responders and regulators is how we say what is toxic, what is dangerous. So from our point of view, as we've been doing more modeling, specifically about ammonia, some of our clients wants to understand the risk associated with shipping ammonia, producing and shipping, is that there is no general consensus about what are the thresholds of concern, right? What is, it's not so much the threshold concern, but that there is such a variety of different behaviors of the pollutant itself, whether it's the NH3 or the total ammonium, right, whether it's dissolved or within the atmosphere, that could become challenging to actually generate simple risk maps, right, for the responders. So from our point of view, we need to be conservative and use relatively low thresholds of concern to be able to generate those statistics, those risk maps, right? The last thing we wanted to comment is modeling could be great, but it needs to be useful. It needs to be integrated into larger frameworks, into systems that allows for the multiple stakeholders and multiple players into an accident and event as to be able to do something about it, right? So we see ourselves as one layer of information. We have developed over the years frameworks, websites, data portals that allows multiple users to log in, visualize information, play with the information, whether it's remote sensing, whether it's current measurements, whatever it is, as well as information coming from all the predictions, right? So that these tools are critical for integrating information, allowing different users to exchange information real time, and be able to make decisions based on this information, right? I'm going to keep it like this. I think it has been very quick. I was asked
Eric,
for presentation.
quick question.
Yes.
Quick question. So, for example, if this model was working live, would it be able to take all the interfaces of local weather data within, let's say, a port where they were operating this system?
Yes. So
okay.
This is already operational in few places.
In which ports?
I mean, not in ports, but for example, in the UK by itself, MCA has schema, for example.
Okay, good. Okay, good.
So,
all right, lovely. We won't take any questions yet because, Eric, thank you very much for that. We want to quickly move on.